Let's move to the second presentation of today's episode is the RPA Ultra Overview, Advantages and Applications. This presentation will be given by Mr. Thomas Rushman. He is a consultant for the Bareiss, and also he has his own company called RTS Rubber Technology and Services. Let me introduce briefly about Thomas. During his studies of the plastics and elastomer technology at the University of Applied Sciences in Würzburg in Germany, Thomas Rushman specialized in the field of rubber and test development. For more than 30 years, Mr. Rushman has been active in the rubber industry and is considered as a leading expert in rubber technology. As managing director of the test equipment manufacturer, Scrubbers, he developed rheological measurement methods that are still used in TA instruments equipment today, and thus had a significant impact on rheological measurement technology in the rubber industry to this day. Since 2020, Thomas has been a consultant at Bareiss Test Equipment, where he supports the development of advanced test methods for polymers and compounds. His experience in the development of new measurement technology provides the decisive impetus for the RPA Ultra from Bareiss, a rheometer that offers unprecedented possibilities. So let's welcome Thomas Rushman to give a talk on the RPA Ultra Overview, Advantages and Applications.
Yeah, thank you. Thank you, Param, for this kind introduction, and thanks for having the opportunity to give this talk today. Thanks for this. Thanks for organization. Yeah, I would like to start immediately with my talk and would give you first a small overview of the agenda, what my plan is today. Today's plan is to give you an introduction about our motivation, why we developed a new RPA or a new rheometer for the rubber industry, and compare this with the current testing standards which are available in the market. I would like to show you more details about the standard test methods which are all included in the RPA Ultra, and for sure give you our new ideas and new development. Means something about steady shear mode. This is a new test method to measure the real viscosity on rubber compounds and polymers. So let us start immediately. So what is a standard test? What we all know since many years in rubber industry, it is a Mooney test. It's a very important test. It's a well-known test, but honestly, it's a patent from 1930, so some years old. And when we are honest, we are not measuring a viscosity which has a unit in Pascal seconds. It's just a torque. What we measure is a torque as a function of time. And that is what you see on the graph on the left side. We have the preheat time, normally 1 minute. We have a test time, which is called the viscosity test. And sometimes people are using additional, for example, 2 minutes after testing, stopping the rotor. We are doing a relaxation test. So this is a typical test what is used for in the rubber industry, and it's called the ML1+4, which means Mooney large rotor, 1 minute preheat time and 4 minute test time. This is a standard test which is well known in rubber industry. But finally, what we are using from this test, and that is what you see on the left graph, we are using this ML1+4 value. It's a 1-point measurement. So we calculating, or Mr. Mooney decided that 8.31 Newton meter are 100 Mooney units, and we call it Mooney viscosity. Again, it's only a torque. If you transfer this Mooney value onto the right side on the real viscosity curve as a function of shear rate, that is what you see here, then it's only one data point of a whole viscosity curve. So you measure only at one shear rate, but what happened in your processing on an extruder, injection molding machine, mixing line, you always have lower shear rates and you also have higher shear rates. But you get no information from a Mooney what happened at this lower and this higher shear rate. So The Mooney, for example, if we go to polymers, the Mooney is an average of molecular weight distribution, and long-term ranging. These are the three main factors which can be changed in a polymer. But Mooney is an average of all of them. So you can have a higher molecular weight, but maybe a broader molecular weight distribution, but it's the same Mooney viscosity. Yeah? So that is something we would like to work out a little bit more. The advantages is well known, but the disadvantages, it is less information. Yeah? So because Mooney is only, and that is what we wrote here, a single point measurement at the shear rate at 1.6 reciproc seconds. Yeah? And this is something we should know. So if we do another standard test, this is our MDR curve, which is a very, very important measurement in the rubber industry. So we need this, for example, here, the S prime as a function of time. That is a very important measurement to characterize the kinetics of a rubber compound. There is no doubt of this. That is something what we need, and we need typical results like the minimum of a curve, the maximum of the curve, the conversion rates, like the conversion like 10%, 50%, 90%, and so on. We can calculate a lot of values here on an MDR curve. But also here, when I go to customers often, then they told me, oh, we make a very small limits here in the minimum of an MDR curve, because we want to be in this very, very small range. And hopefully when we are in this range on the minimum, in the tolerance curves of the minimum, then we have no problem in production. And then when I asked them, okay, how often does that fit? Yeah, and they told me, not so often. They still have problems. Yeah, the tolerances are very small and everything is fine on the curve, but they have a lot of problem in production. What is the reason? The reason is easy to explain, because although the minimum curve is done at one shear rate, normally we are running at 0.5 degree of arc and at a frequency of 1.67 Hertz. So that means also here we are at one shear rate. So you have no information what happened at lower shear rate again and what happened at higher shear rate. Yeah. And the second one is normally we make cure curves at 180 degrees Celsius, which is far away from the processing temperature. For example, when a material is coming out of an extrusion line, we are around between 90 and 110 degrees Celsius. And so you should not expect, when you measure only at one shear rate and on a different temperature, which is far away from your processing temperature, that this will give you an information about the processability of a rubber compound. So we need some more information, and that is what I would like to explain during this talk. So we have these two measurements. We have the standard measurements Mooney. We have the minimum of the cure curve, and again, only one shear rate, and on the cure curve, we are far away from the processing temperature. So that is something we want to go on. Before I go to the processing, I would like to give you an information how a rheometer is working. It's an MDR, an RPA, or a rheometer. So on the right side, you see on the bottom, you have the stepper motor or motor. Then you have the lower die with the heater. Then in the middle, you have our rubber sample, which is sealed, completely sealed. It's a closed cavity, we call it. Then you have the upper die, and on the top, we have our torque transducer. So what you also here see, when we are talking about the modulus later and about viscosity, we don't measure a modulus or we don't measure viscosity. What we measure is a torque. That's all. Yeah? So what we have on the left side, on the sinus curves, you see that we have a sinus curve of the strain. That is what we apply with the motor. And we get an answer on the torque transducer on the top, the black line. That is what we get from our torque transducer. Yeah? And you see we have the maximum, the minimum and maximum of our torque curve. This is something about the stiffness of the sample. And what we have a phase angle because we have viscoelastic properties. This is our phase angle. And that is what we measure. Yeah? And how do we calculate a shear modulus from this data? That is something what I put here in this formulation. So we measure a torque value, which is called here S star. We divide it by our strain signal. This is what our motor is giving, for example, 0.5 degree of arc. And we multiply it with a die factor. This is because of our cone cavity. This is what you can read in every rheology book. Is depending on the diameter and the cone angle here, what we have in our die. So the shear modulus is our torque value, what we measure, divided by our strain, multiplied by this factor. And when we have this shear modulus, we can calculate our dynamic viscosity with this shear modulus. That is what you see here. And our omega is 2 pi f, the frequency. And then we have the dynamic viscosity. So this is a small overview that a lot of people think, oh, we are measuring viscosity or something like this, but this is not true. What we are doing is we are measuring torque and we are calculating the shear modulus and we are calculating the dynamic viscosity. That's all. So which typical test methods are available in an RPA? So for example, we have an isothermal test. We have a non-isothermal test, we have a frequency sweep, we have a strain sweep, we have LAOS, which means large amplitude oscillatory shear. It's also a strain sweep, which is going to very high strains, that's all. And then finally, we have a steady shear mode, which I will explain later. So let's start with a typical isothermal test. I think this is what we know. On the left side, you see a typical cure curve. The red lines are the typical gates, the tolerance curves or the tolerance limits, what we have for minimum, maximum, TC10, TC50, TC90. This is what we need for standard quality control and which is very important. Yeah? And for sure, the RPA Ultra can perform all these tests. But also what we can do is we can run at different temperatures. And then we can calculate the conversion and we can calculate the conversion rate and we can do some more enhanced calculations like order of reaction, conversion rate constant, activation energy, and we can calculate heating time, for example, of your 6mm plates. Oliver mentioned something before on samples which we need for hardness or 2mm for tensile test and on. That is something we can calculate the heating time very easily. Unfortunately, because of time, this could be another session, yeah, only talk about kinetics and the opportunity, but I just want to point out, if somebody is interested, it would be a pleasure. They can call us whenever you want, and we can go more in detail about isothermal kinetics and discuss here more. The second one, what I wanted to show, because in rubber industry, the processes are not isothermal, they are always non-isothermal. So let's run some non-isothermal curves on an RPA or on an MDR. So what we can do is we can run with, for example, 2, 3, 5, and 10, 20 Kelvin per minute. We can run from 80 degrees, here an example, up to 200 degrees. And what you get is also here the answer. It's a S prime in deciliter as a function of time. So what happened? The torque is decreasing, it's clear, because temperature is increasing. And at a certain time or in temperature, it starts curing and you get also such a curves like a cure curve. And you can also calculate the minimum and the maximum. Yeah? And this can be done again on different heating rates. The reason for this is, first, a nice example on a natural rubber compound. On the right side, you see an isothermal curve where you see nothing really special. Yeah? But when you look at a lower temperature, with around 60 to 80 degrees, the torque is increasing, but the temperature is also increasing. So normally we would expect that the torque will be decreased. So this happened, and this is a temperature which happened in your mixer line, for example, when you put the natural rubber polymer in the mixer. And this is something like some thermodynamic effects, what you see here. and that will definitely have an impact of the mixing behavior of your compound. Yeah, and this is sometimes with natural rubber compounds. It is less with natural rubber when you have constant viscosity types, but with SMR you see very often this type of effects, which are sometimes available in process and sometimes not. But again, this gives you this additional information when you are running a non-isothermal test instead only running an isothermal test. Also for the non-isothermal test, this blue curve, orange curve and gray curve are the three heating rates, torque values, when we plot the conversion as a function of absolute temperature. Yeah? And the black curve is connected TC90, TC50 and TC10. And then you see here very nicely that you can calculate your activation energy depending on the conversion. And you see here nicely that you have a two-step reaction. Yeah, so if you, for example, want to see on competition compounds, see what happened of the kinetics, you see much more than you see only on an isothermal curve. So I want to motivate you. Isothermal curves are very important, but if you want to go more in detail, sometimes it's very helpful to run a non-isothermal test. And it would be a pleasure if we can help you with test plans and how to calculate all this data. Would be very would be great for us to help. So going the next step, going back to processability, going back to viscosity. So we discussed about kinetics, about the chemical behavior of your compound. Now we're going back and want to have the physical properties, means a frequency sweep. What is a frequency sweep? A frequency sweep means a constant strain, for example, 0.5 degree of arc, and what we have is variable frequencies. For example, from as RPA ultra can perform from 0.00, we missed a zero, it's 0.001 to up to 100 hertz, but a typical one is 0.01 hertz, because 0.001 needs a lot of time. Yeah. And this is something where we definitely can perform very nice results. And a typical plot is G prime and G double prime and the dynamic viscosity. And that is what you see here in the graph. The orange one is G prime, the gray one is G double prime as a function of shear rate. And what you see, the blue curve, and this is the dynamic viscosity as a function of shear rate. Remember, when we performed the Mooney test, we only had this one data point and nothing else on information. This is what I want to see here. Why is it so important? Because when you're measuring a Mooney, the slope of this viscosity curve can be completely different. You have no information about this. And this slope of this viscosity curve has a huge impact of the processability of your rubber compound. Yeah, that is the reason why Mooney is so limited on information. So again, how to calculate it? So G prime, again, you remember, we measure a torque, we divide it by the strain, and we multiply it by our die factor of our cone rheometer. Also the same for G double prime, and again, also for the dynamic viscosity. So this is something what we can do. So if you have the torque values as a function of strain, you can do this very easily every time to calculate modulus and dynamic viscosity. A nice application where we can use this frequency sweep is when you plot G prime and G double prime, and when both of these curves has a crossover point. That means where G prime and G double prime has the same value. If you can find this value and if you compare it, for example, with different polymers, so if this point is moving to the right side, you have a lower molecular weight. If it goes to the left side, you have a higher molecular weight. If it goes down, you have a broad molecular weight distribution. And when it goes up, you have a narrow molecular weight distribution. And this is something which gives you a real information about structure. So it's not only an average between molecular weight and molecular weight distribution. No, it really gives an information. And this is a well-known polymer test, and which can be also used for rubber compounds. I will show you later some more examples on, for example, EBDM. So again, when we have these two examples, EBDM and EBD1, they both have more or less the same Mooney viscosity. If we plot the dynamic viscosity and look at this, when we are in the range of the shear weight of Mooney, yes, they are definitely the same. We see a little bit differences here and here, but it's a log scale. Yeah? So we will see more if we plot again G prime and G double prime. Yeah, so you see on the orange one, you have this crossover point, which means molecular weight. Yeah, it's on this position. And the blue one, you see, you have to make much lower shear rate. So the crossover point being the out of the graph, it was on the left side. So there is a huge difference in the structure of these two polymers. But if you buy an order with Mooney viscosity, it's the same, but this will have complete different behavior during the mixing process. It will have complete different behavior on injection molding, transfer molding, extrusion. So you will be definitely not happy about this. Another indication of this will be the tangent delta. Maybe you heard of the tangent delta. The tangent delta is a calculation, is a ratio between G double prime and G prime. So it gives you something about the elasticity, and it gives you something about the viscous behavior of the compound. Yeah, so I call it always, it's an information about your viscoelastic properties. Yeah? And over here, you see, when you go to a lower shear rate, and then you see huge differences in tangent delta. Again, both have the same Mooney viscosity. So if you're running frequency sweep, and maybe you already have an RPA in your company, and if you want to see differences in structure of polymers, please go to this lower shear rate. Here you can really nicely differentiate if they have the same structure or not. Yeah? This is a very, very important information. And this is helpful with this type, with a frequency sweep. We can perform very easily, and their RPAs are very, very, very strong. So the next one would be the strain sweep. In the strain sweep, now the frequency will be constant, for example, at 1 Hertz or 1.67 Hertz or 0.1 Hertz, and we make variable strains. Yeah? For example, here we go from a very, very low strain up to a very, very high strain. Yeah? And then you see a typical curve of a strain sweep. It's called G prime, again, the shear modulus as a function of strain. When you go for at a very, very, very low strain, the modulus is independent of the strain. If you remember, we said we calculate the G prime is the torque divided by the strain multiplied by the die factor. So if we have torque divided by strain, so we double the strain, and if we double in the same time the torque, so modulus is the same. So we are in the linear viscoelastic regime, and which gives you very, very nice shoe figures. Yeah? So that is something what you see here. If you increase the strain, more or less we go to the non-linear viscoelastic regime. That means you are increasing the strain, but torque will not increase in the same time. And then when you go to a very, very high strain, this means around 1000% of strain, you go to LAOS. It's called LAOS. It's large amplitude oscillatory shear. I will explain a little bit later here in this presentation. So this is something where you can see what we have. The laser shoe figures are significant different, yeah, and the LAOS test is very, very sensitive to another component which is important on polymer. It's the branching of a polymer. Yeah, remember in the beginning we had this triangle on the Mooney, Mooney is an average of molecular weight distribution, and long chain branching. And here we can differentiate very nicely the long chain branching of polymers, and that is what I would like to show here. The next speaker will be Henri Bareiss, and you see he published something. It's in 2008, so it's some years ago, where the people found out a lot of nice information. Just a little bit theory before we go back to application. So the red line is the sinus curve of our motor. Yeah, and normally we would expect as an answer the blue curve. Yeah. So you put a sinus on your sample and you would expect a sinus curve as an answer for sure with a phase angle, yeah, because we have viscoelastic properties. But the real answer was a black curve. So there is a lot of information inside which we want to work out a little bit more in detail. So if you plot here the shear stress as a function of strain, you get such nice curves, yeah, and you see there's some nice information inside. So the next plot would be more or less the same. We only change the x-axis from the strain to the strain rate. Yeah, so the time is also a very important information here. And then you have such nice graphs. And we found that this fits very, very well for rubber polymers. That means if you plot the shear stress, again, as not as a strain, we plot it as a strain rate. And if you have linear polymers, you have something like here, these called secondary loops. And as soon as you have some small branching inside of your polymer, these secondary loops disappear. Yeah? And if you have a lot of branching, you see you have these broad Lichaux figures. Yeah? And this is something very, very nice and information what these gentlemen found already in 2008 and very helpful, and which I know polymer suppliers, for example, are already using this every day. But yeah, they only give the information on Mooney. So for sure, would be difficult for you in industry always to see, oh, do we have secondary loops or not? So it's not possible. So for this one, the LCB index was born, or it's called long chain branching. Yeah, I would like to have information about the long chain branching of a polymer. And this means what we are using is the Fourier spectrum, the higher harmonics, yeah, of our torque signal. And if these values are negative, we have a linear polymer. And if it gets more and more positive, it is a branch polymer. So this can be used also with control limits, so that the supplier, or if you have a different supplier for the same polymer, you can double check if the branching behavior is the same, because branching is a very important parameter for the mixing line, for extrusion, for the viscoelastic properties. This is very important and very, very sensitive is this last test. So on our example, I would like to show again, remember both EBDMs have the same Mooney viscosity. And when we plot on the left side, you see G prime, the blue one, and the gray one is G prime as a function of strain. And the yellow one and the orange one is a tangent stellar as a function of strain. And you see at a very high strain, a huge difference in tangent stellar. Remember, tangent stellar is the ratio between G double prime and G prime and gives you an information about viscoelastic properties. So here we have the second one. So if you have such an instrument, or if you're interested, and that is what the RPA Ultra can perform very, very nicely, you can run a frequency sweep and check tangent stellar at low frequency, at low shear rate, and check the tangent stellar at a very, very high strain value. And then you already have a nice information about this. And for sure, we also can plot these very nice curves with our RPA Ultra. And you see the blue one has this broad character, which is a branch polymer. And you see the orange one, which has nearly secondary loops. And this is a linear one. And you see this on the LCB index. One is -0.9 and the other one is +1.4. So you have differences in branching. Yeah. So just to summarize, we have two polymers which have nearly the same Mooney viscosity, but they are different in molecular weight distribution, and long-term branching. So you cannot replace it one by one. Yeah. But the Mooney is the same. But please be careful, and yeah, please go ahead and run this test. And honestly, this will take around 10 to 15 minutes, and then you have a real information about your polymer. Yeah, that's very, very important. The next one is the steady shear mode. So what does it mean, steady shear? You see here something like rotation. So what we discussed all the time now on a frequency sweep, on an isothermal test, a non-isothermal test, when we're talking about strain sweep, we always make an oscillation, yeah, plus minus of degree of arc. But here we start now and make a rotation of the lower dial. So remember, like a little bit Mooney when the rotor is rotating, yeah? And that is what we are doing now with the RPA. And then, for example, here is 10 rotations. You put a compound in, and then we measure the torque as a function of time or degree. So when we make 10 rotations, we have 3,600 degree of arc, because 360 multiplied by 10, these are the straight what we are doing. And you see we have this small overshoot, and then we are going more and more in a flat condition. Yeah, that's a very important information here. So how does it look on our motor? Well, the motor starts rotating, yeah, from 0 to 3,600 degree, 10 rotations in, for example, 500 seconds. And we can do this in different times, which will make different shear rate. Yeah, and that is something what you see here. So when we, for example, there are some instruments in the market who can do only plus minus 90 degree of arc, or there are some instruments in the market who can do 360 degree of arc. Yeah, but if you look here on the right side on this plot, these, yeah, what is it, color yellow or green, if you only go to 90 degree of arc, you are not in steady shear. Yeah, so this is something because of our complex polymers, which we are using in our industry, and for sure because of the fillers what we have in the compound. If you're running 360, it's definitely better, but still not enough. So we need more or less 10 and more rotations that we are in a real condition, and this is close what happened in your extrusion line or in your injection molding machine. Yeah, and that is something, our idea to make an instrument where we can really make process simulation. So what we definitely need, we need more times rotation. It's not enough for 90 degree of arc. It's not enough for 360 degree of arc. That's very, very important information. So when we are doing the motor, what I mentioned before, up to 3,600 degree of arc means 10 rotations at different time, means different speed, means different shear rate. So we are running at, for example, 0.1 reciproc seconds, 1, 10, 100, and 500 reciproc seconds on shear rate. Yeah? And then you get this curve. We have this overshoot, and then going in this steady shear conditions. So when we plot these steady shear conditions and we transfer it on the right side and plot the viscosity as a function of shear rate, we get these nice, very, very nice viscosity curves. So now we have not longer a dynamic viscosity. Dynamic viscosity is always oscillating, but in your machine outside, it's never ever oscillating, it's rotating everything. Yeah. So this is coming much closer to reality than what we measured before, or what is done on a frequency sweep. Another very important message, what I want to say, another opportunity to measure viscosity is a high pressure capillary. But when I'm discussing with these guys, everybody's telling me, oh, he's doing a lot of corrections, and yeah, so I'm not a friend of all these corrections, yeah, because what we are doing here, we have the die constant of our cone rheometer. We are measuring a torque. We multiply it with this die constant, so we have the shear stress. And then we take the shear stress, calculating by the shear weight, and we have the viscosity. Done. No correction. These are really measured values, only calculated with the geometry factor of our die. So there's no corrections needed. Does it work? Yes, it is. So we compared it. On the left side, we used a very easy linear polymer. Yeah? And then we run a dynamic viscosity test, which is here the blue line. And we run the steady shear viscosity test, what I mentioned before, with these different shear rates, with these different speeds. And because of the Cox-Matz rule, because it's a linear polymer, both should be on the same. And it is, though it works perfect, our RPA Ultra. When you go to a rubber compound, the Cox-Matz rule cannot work anymore because it's depending on fillers. Yeah. So, for example, here, if you will use the dynamic viscosity of a rubber compound, it's the blue curve. If you run a steady shear viscosity on the rotation, which is close to the reality, what happened in your machine, the viscosity is on a complete different level. And for example, if you would like to use something for simulation and you would give somebody the dynamic viscosity, it will definitely fail. He will have no chance to simulate the process. Yeah? So dynamic viscosity is not able to support simulation. Yeah? That's important. So you definitely have to go to this steady shear viscosity. I would like to give you a real example what we did here in Germany with a group together. You see on the colors, maybe this is from Evonik. It was Freudenberg, Continental, included a lot of companies. And we used some of these compounds. Yeah, though this is, we changed the polymers. It's a CB22, which is a linear BR, and the 1220, which is a branch polymer, for sure, compared with plus the SBR, and with different fillers. Because it's a lot of compounds, we are focused on 4 compounds. Yeah. So you see, sample number 4 and 7 have the same polymer, the linear Buna, but the first one has the silica silane, and the 7 has the carbon black. 11 and 14, the same filler combination, but a different polymer, the branched one. And we wanted to see how can we describe the viscosity, the real behavior, processing behavior of such compounds. Which instruments can do this? And honestly, we worked a lot of years. You see, we published already something in 2017. So because we failed all the time. Yeah. One very nice method is the Garvey. Yeah, maybe. I'm pretty sure a lot of people of you know Garvey. So it's an extrusion test where you can see and where you give an order how good or how bad the extrusion result is. Yeah, and for sure for this M4, which has a linear polymer and it has a silica silane, it's horrible in processing. Everybody knows. And the opposite is, for example, sample 14, where we have a branch polymer and we have a nice carbon black, which is much better. Yeah? And this is also here in this ranking of these Garvey ranking. You can see this very nicely. So the idea was now, can we make these correlations? So when we look on these 4 samples, 4, 7, 11, 14, yeah, remember 4 is this one with a linear polymer, and with this silica silane, you see these very, very bad Garvey results. Yeah, and on the other side, you see 14, which has a very nice surface. Yeah, so, but honestly, no instrument. We did a lot of dynamic tests. We did a lot of high pressure capillary emitter, but nobody really could find a nice method. So we run a steady shear test, and I would like to explain you this graph. So what you have here is the shear stress as a function of shear weight. Here are our 4 samples. Remember, so the green one, the orange one is sample number 4, and which has the very, very bad processing behavior on Gavi because of linear polymer and silica silane. Yeah? And if you look, for example, in 14, it's much better, a bronze polymer and a carbon black. And you see, if you go to shear weight, what normal instruments have, if you go to lower shear weight, this means Mooney. Look at the shear weight at 1. This is Mooney. Mooney gives the highest Mooney for sample number 11. Yeah, but this is in Gavi. There's a complete different information. When we go up to 500 reciprocal seconds, if we go to a very, very high shear rate, and then we have the nice ranking of Gavi again. So you see on the left side, we have our shear stress at high shear rate compared to the Gavi ranking. We get a very nice correlation. So you see all compounds you are flattening here at higher shear rates are good in processing, which are increasing more and more and more and more at high shear rates. These are very bad in processing. So this is the first method and the first results what we saw in industry, that we can really simulate the processing behavior of compounds with this steady shear method on the RPA Ultra. Yeah. And that is something where a lot of people are very exciting now, and where we are going on with a lot of tests where we want, or which is planned. So this is something what I wanted to discuss and wanted to present today. For sure, all dynamic tests are important to give you an information about polymer structure, give you an information about molecular weight distribution, and long-term branching. But if you really would like to have an information about the processing behavior, you need to go to a steady shear mode. The RPA Ultra is able really to perform both dynamic tests and processability tests. And that is something what we discussed, and I told you before, what we developed together with industry. There's a lot of people, and we want to say thanks again here. And again, it would be more than a pleasure to go in touch with you and run some samples for you, introduce more, go more in detail, and discuss hopefully soon personally. Thank you very much for this, for your education. Thank you.
Thank you very much, Thomas. Very informative presentation on the RPA and also applications. Fantastic. Thank you very much.